Our galaxy is called the Milky Way. We often think of it as a faint band of light across the sky that can be seen from dark locations. That band can be either an outer arm of the Milky Way or toward the galaxy's center, depending on the time of year. But the Milky Way isn't just that stripe in the sky. Almost everything we can see in the night sky belongs to the Milky Way, even if it isn't along that band. A galaxy is basically a group of stars, gas, and dust in space. The number of stars in a galaxy varies greatly, from just a few million to up over 1 trillion. Our Milky Way has billions of stars, so it's pretty average. We can estimate the number of stars in a distant galaxy by the size and brightness of the galaxy. It isn't possible to count individual stars as far away as galaxies are. These images are all photos of objects within Charles Messier's catalog. We talked about Messier briefly before. His catalog is a list of dozens of objects he found in the sky while looking for comets. You may notice that many of these pictures show types of objects we've looked at in this class. We see globular clusters, open clusters, emission nebulae, planetary nebulae, and spiral galaxies. There are also other types of galaxies beyond just spirals. People in Messier's times, though, did not understand that these other galaxies were not part of the Milky Way. They just thought that galaxies were nebulae within the Milky Way. In 1920, the National Academy of Science hosted a debate about what were called spiral nebulae, challenging people to argue whether they believed these objects were part of the Milky Way or whether they were what were called island universes outside the Milky Way. The first person to prove these other galaxies were totally separate from the Milky Way was Edwin Hubble. Using Cepheid variable stars, he attempted to calculate the distance to the Andromeda galaxy. Even though his numbers were somewhat off, he was able to prove that there was no way that Andromeda was part of the Milky Way. These same Cepheid variable stars also helped to determine that distant objects were accelerating away from us, which is part of the evidence for the Big Bang. We'll look at this more in the next lecture. Cepheid variables are a type of object called a standard candle. They are objects of known brightness that can be used to determine the distance to far-off objects. In the case of Cepheid variables, remembering that the pulsation rate determines its brightness. Another type of standard candle is the type 1A supernova. This type of supernova explosion always explodes with the same brightness. Standard candles are important because if we know how bright an object actually is, we can compare that to how bright they look and thus determine how far away the object is. Here's a more everyday example. Imagine you have a lamp with a 100-watt light bulb in it. If you stand very close to the bulb, it's quite bright. But if you walk back from the light, the farther away you get, the dimmer the bulb looks. The bulb is still putting out the same amount of light. It just looks dimmer because you're farther away. The same process helps us to determine the distance to galaxies that have these standard candles within them. Let's try to spot one galaxy of each type in this image of the Hubble Ultra Deep Field. In this image, everything you see is a galaxy. These aren't stars, but are far-off galaxies. Let's look at this image first. Can you tell what type of galaxy this is? Hopefully so. This is a spiral galaxy. This is more or less what the Milky Way looks like. There are two types of spiral galaxies, and we'll look at these in a moment. How about this one? There aren't any spiral arms here, but can you see that it is oval-shaped? This type of galaxy is called an elliptical. Some of them are more rounded, some of them are more stretched out into a more oval shape. Now how about this one? This picture is kind of small and hard to see, but hopefully you can tell that this is neither spiral nor elliptical shaped. This one has a rather obvious and simple name. The galaxies that are neither spiral nor elliptical are called irregular. Here are several images of galaxies. Can you tell that all three of the ones at the top are spirals? The first two are face-on spirals, though the spiral arms are a little easier to see in the second one. The third one is an edge-on spiral that we're looking at from the side. Notice this dark line across it. That is a dust lane where new stars are forming, and those are only seen in spiral galaxies. The two on the bottom left are ellipticals. The first one is pretty circular, and the second one a little bit more oval, stretched out in the left-right direction more than the up-down direction. The last image is of an irregular galaxy. It doesn't fit into either of the other categories. More than half of all galaxies are ellipticals. They basically look like massive blobs of stars. They can be more rounded or quite elliptical in shape. The ellipticals are much older than spirals and thus have very little gas and dust remaining. Because of this, they also have no new stars forming. Some ellipticals are enormous, but many are quite small. The most numerous galaxies in the universe are dwarf ellipticals. So the biggest and smallest galaxies are ellipticals, meaning that spirals are more middle-sized. Here is an enlarged image of an elliptical. These galaxies are all bulge, just a large spheroid. There are no disk components to these galaxies. The major way you can differentiate an elliptical galaxy from a globular cluster is that in the galaxy, you can't differentiate individual stars throughout the structure because the galaxy is so far away, it just looks like uniform brightness. You can see lots of individual stars in the globular clusters that orbit our Milky Way. Spiral galaxies are flattened disks with one or more spiral arms. Our Milky Way is a spiral, and more specifically, probably a barred spiral. Our solar system is located in one of the spiral arms. Our Milky Way seems to be a spiral-shaped galaxy, similar to Andromeda pictured on the right. Andromeda is the closest large galaxy to our own. When we look towards Orion, seen in the sky map, a lighter strip showing us the location of one of the Milky Way's spiral arms. This is a composite image showing what the Milky Way looks like in the direction of the galactic center. This is not the entire galaxy, and a photo of the entire galaxy does not exist. It would be impossible for us to take a photo of the entire galaxy from inside the galaxy. Notice the brighter area in the center. That's the galaxy's core or nucleus. It's mostly obscured, though, by dark bands of dust between our location and the core. Light cannot penetrate through this dust, so we see just darkness. Again, this is the Andromeda Galaxy, not the Milky Way. You can see two of Andromeda's satellite galaxies also included in this photo. If this were the Milky Way, though, our solar system's location would be indicated by this arrow, far out from the center of the galaxy, out in one of the spiral arms. To describe the Milky Way, perhaps the easiest way to think of it is to imagine a fried egg. The bulge in the middle, the yolk, would represent the galactic core, while the white part would represent a relatively flattened disk where the arms are. However, unlike the egg white, the galaxy's flattened disk is not solid from edge to edge. There's a lot of empty space between the stars and even between the arms. The galaxy is huge, about 100,000 light years in diameter and between 1 and 3,000 light years thick. If the sun were the size of a period at the end of the sentence on your paper, the Milky Way galaxy would be the size of the entire United States. As I mentioned, we can't take a picture of the entire Milky Way from inside it. But if we wanted to shoot a picture from the outside, we'd have to be able to get a spacecraft above the plane of the Milky Way to a height equal to our distance from the galactic center. How long would it take to get there? Well, first, Let's imagine we have a spacecraft that can travel at the speed of light, 186,282 miles per second. What do you think it would take? 2 months? 5 years? 250 years? 30,000 years? Or 5 million years? Take a moment and make a guess. The Sun is about 8,500 parsecs, or 30,000 years from the galactic center, and that's traveling at the speed of light. New Horizons, the fastest spacecraft launched, traveled at about 10 miles per second. To travel 30,000 light years, or 1.8 times 10 to the 17th power miles, the New Horizons spacecraft would take 570 million years to get there to snap a photo. No battery could last that long. Here are a few images of some galaxies that look pretty similar to what we think the Milky Way looks like. We think it's roughly 100,000 light years across and has between 100 and 400 billion stars. That's a pretty wide range, but it's hard to narrow down since the light from many of these stars is completely invisible to us here on Earth, blocked by the large amounts of dust in the galaxy. Just like the planets orbiting around the Sun, our Sun orbits the center of the Milky Way. It takes about 250 million years for our Sun to travel its path around the galaxy. So the last time our solar system was in this area of space, dinosaurs were just getting started on this planet. Here is another spiral galaxy, similar to the Milky Way, seen from two different views. The first image shows it face on, with the spiral arms visible within the stellar disk. The second picture shows the galaxy edge on, meaning that you're looking at it from the side. Here, you can more easily see the dust lane, a thin, patchy disk of gas and dust that is fuel for the next generation of stars. The major components of spiral galaxies are the bulge in the center, the disk that surrounds the bulge, and the halo is the area both above and below the plane of the galaxy. Here's another image of the same information. The galactic bulge surrounds the galactic center, and this bulge is home to mostly older stars. Moving outward is the galactic disk, full of gas and dust, called the interstellar medium, or ISM, and the spiral arms. Though there are old stars here too, the gas and dust in this region means that we also find young stars here. Another type of star cluster, called open clusters, live within the galactic disk. The galactic halo surrounds everything and is home to the globular clusters and other very old stars. In the bottom images, you can see the differences between the two types of clusters. Open clusters are dense collections of stars. However, can you see that in this globular cluster, we have many more stars that are even more closely packed together? Globular clusters are very old, and they almost look like mini galaxies. In fact, some of them may be the remnant cores of galaxies that got consumed by their parent galaxy. There are 3 different populations or types of stars. Population 3 stars are the oldest types of stars that would have existed shortly after the Big Bang, consisting only of hydrogen and helium. They don't appear in the graphic as no more stars of this type exist. They all died long ago. Population 2, sometimes just called Pop2 stars, are the older stars. These are called metal-poor stars, meaning that they have only very small amounts of material other than hydrogen and helium in them. Even though there are a lot more nonmetals beyond hydrogen and helium, astronomers call anything heavier than helium a metal. These stars are typically found in the nuclear bulge, the galactic halo, and in globular clusters. These stars are typically redder in color and are cooler stars. Population 1 or POP1 stars are much younger than their POP2 cousins. They are located mostly in the spiral arms and in the galactic disk. They burn, on average, much hotter and bluer than the POP2 stars. Our Sun is a population 1 star. Though there are many nonmetals and metalloids on the periodic table, astronomers have a more simplistic way of viewing the table. As almost all normal matter in the universe is hydrogen and helium, astronomers refer to all the heavier elements collectively as metals. Here we see another spiral galaxy. Notice how the center portion of the galaxy is much more red and yellow than the spiral arms. The bluer stars in the spiral arms are much younger than the reddish stars in the center. These blue stars are fed by the gas clouds in the disk. This doesn't mean that all stars in the arms are blue. Remember, our own Sun is yellow and out in this spiral arm area, but the average star in the arms is younger, hotter, and bluer than the average star in the bulge. Irregulars are those galaxies that do not fit into any of the other categories. They are just chaotic mixtures of stars, gas, and dust. These irregular galaxies are often found near other galaxies who are gravitationally distorting their shape. Here's another image of an irregular. No spiral arms, no regular oval shape, just a lot of random splotches around. The brighter blue-white area is a star-forming region. Again, much of what we believe to be true about our galaxy is speculation. We know more about other galaxies than we do about our own. The structure of the Milky Way is difficult to determine, not only because we are inside of it, but because it's difficult to obtain precise distance measurements and that our view of much of the galaxy is blocked by gas and dust. Think about driving through fog. A thin layer of fog makes it difficult to see very far in front of you horizontally, but you can still easily see distant objects that are above the fog layer. Though we can't see through the galaxy to the center, we can see globular clusters that group up above the galactic center. With just a little bit of geometry, we can actually determine how far away the center of the galaxy must be. We have several ways to discern the structure of the Milky Way from what we can see, even though there is much we cannot see. As with the globular clusters, we can select bright objects that are visible to determine their distance and how they are moving. Another major way is using wavelengths of light other than just visible light. Interstellar extinction makes us unable to view the galactic center in the visible light, but it is very clearly visible if we use other parts of the spectrum. We will look at this more closely momentarily. Finally, we can look at how quickly other objects are moving relative to our position, and we can determine mass distributions throughout our galaxy based on gravitational interactions between objects. You might be wondering how we can measure distances to these far-off objects. We've talked about the parallax method before, but that only works for objects that are relatively close to us. We need to be able to measure distance accurately to much farther off objects, as the Milky Way is huge, 100,000 light-years across. There are a couple of easy ways, one using variable stars, but Herschel didn't know about these methods in his time. Take a look at this set of images. Can you see how the star dims over time, brightens back to its original luminosity, and then begins to dim again? The rate at which this dimming and brightening occurs can help us determine distance. One major way we can determine distance to far-off objects is by using a type of variable star called a Cepheid variable. These pulsating stars were discovered by American astronomer Henrietta Swan Leavitt, and she realized that the brightness of these stars varies over time in a very regular way. Notice the two graphs on the right. The first star goes through about 5 cycles in 3 days, while the second star goes through 3 cycles in 9 days. Leavitt realized that the time period was directly proportional to the star's luminosity. That means knowing the brightness of the star from Earth and the star's true luminosity from its pulsation rate, we can calculate the distance to that star. Now remember, there are 2 different types of clusters. These more spread out, younger clusters called open clusters, and the more densely compacted, older globular clusters that live in the galactic halo. Harlow Shapley, another American astronomer, noticed that though globular clusters can be seen in all directions, the vast majority of them are on one side of the sky, in the direction of the galactic center. They are more heavily concentrated there because the clusters, like everything else in the galaxy, orbit the galactic center. Globular clusters have lots of Cepheid variable stars, and he used their pulsation rates to determine distance to the galactic center. I said that in the direction of the galactic center, we can see very little visible light due to gas and dust that blocks that wavelength of light. But if we want to see through that dust, what kind of light should we use? Remember, visible light, the type of light that we can see, is only a tiny bit of all the available light produced by stars. Each type of light, from radio through gamma, has different capabilities regarding penetration through dust clouds. Here are 10 different images of the same area of sky, looking toward the Milky Way's center. Notice that the third from the bottom, there's a lot of dust and not much to see. This is the optical wavelengths, meaning visible light. Notice how we see a whole lot more detail in each of the other areas of the spectrum, whether longer or shorter wavelengths. Now let's look at 2 different types of infrared radiation. The near-infrared image shows us the very clearly seen nuclear bulge. You can still see a bit of the dust laying in front of it, but the full galactic plane is visible. You can also see the 2 Magellanic clouds below the disk. These are a couple of small satellite galaxies that orbit the Milky Way. In the far infrared image at the bottom, you can see even more detail, as this wavelength of light is barely absorbed by dust at all. Here are a couple more spiral galaxies that probably look similar to our own. The Sombrero Galaxy we see edge on. Though we can't see the spiral arms, we can see the gas and dust lane around the outside. NGC 2997 is a face-on spiral, and we can see its dust lanes as dark lines between and within the spiral arms. There are a couple of side-by-side images also taken of the galactic center. In the first image, we see an optical visible light image. Lots of dark dust blocks out where the actual center of the galaxy is. In radio waves, however, that extremely bright spot on the right is readily recognizable. There are structures in the centers of most, if not all, large galaxies called supermassive black holes. The types of black holes we talked about in Unit 3 may have a mass 10 times heavier than the Sun. These are hundreds of thousands or millions of times heavier. This is an image showing several stars that are nearest our galaxy's black hole. They orbit the black hole in much the same way as the Earth orbits the Sun. Go through the PowerPoint in slideshow mode and activate this link to see these stars closest to the galactic center orbiting what appears to be nothing. You can tell that these stars are orbiting something, but when you zoom in, they don't appear to be circling around anything at all. The object at the center of our galaxy is a supermassive black hole. The name of the Milky Way's supermassive black hole is Sagittarius A star, and it's abbreviated like this. The name Sagittarius is in it since the black hole is in the direction of the constellation of Sagittarius. You can see the area around the black hole here as imaged in radio waves. Look at just how active the black hole is in radio wavelengths. Zoomed in, you can see arcs of material coming out from the center as other objects are gravitationally disrupted by this beast. Using a system of telescopes called the Event Horizon Telescope, we have now imaged the supermassive black holes in the center of two different galaxies. First, the one in galaxy M87, then Sagittarius A star in our own Milky Way. Orbital paths taken by Milky Way objects depend on where in the galaxy they are located. For objects in the galactic plane, within the galaxy's disk, these stars have elliptical but nearly circular orbits and revolve within the plane of the disk. These stars orbit the galaxy nucleus in much the same way as the planets in our solar system orbit the sun. However, objects located within the galactic halo have much more inclined, randomly oriented orbits. This is similar to Oort cloud objects within our solar system that can orbit the sun coming from any direction. Think back to when we talked about planet revolution times. We talked about the fact that Mercury was the fastest planet, not just because it follows a smaller orbital path around the sun, but that it also travels at a faster rate of speed. Revolution in our galaxy is the same. Our sun orbits the galactic center at a speed of about 220 kilometers per second, and it takes about 250 million years to complete a full orbit. However, this is not true of all stars. Stars located closer into the center of the galaxy actually orbit faster, and the stars farther from the nucleus travel more slowly. But though the distant stars orbit more slowly than the ones closer in, they are still traveling way faster than they should be. These outer stars are traveling so rapidly that the whole galaxy should be flinging itself apart. Imagine you have a pile of sand on top of a plate and you spin around really fast. The sand would fly out away from you all over the place. The galaxy doesn't seem to have enough mass to provide enough gravity for it to hold itself together. Our best estimate about the mass of the entire Milky Way, based on rotational speed, is about 1 billion solar masses within the disk and 1 trillion solar masses if we include the material in the halo. However, when we sum up all the individual objects we can measure, it turns out that we are missing a lot of mass. We aren't sure why the numbers are so far off from what we would expect. It is thought that maybe there is a large amount of something called dark matter out there that is providing enough gravity for the galaxy to hold on to those super fast outer stars. You could compare it to a kid's merry-go-round spinning way too fast. The kids would go flying off. If not for the dark matter in our galaxy, the stars would go flying apart also. Vera Rubin was the first scientist to realize this discrepancy. She realized that there must be a lot more matter in the galaxy than what we can see. In fact, galaxies appear to be mostly made of this material we now call dark matter. This missing matter is called dark matter. Number one, because we can't see it. It's dark, not reflecting light towards us. However, it must provide mass, and thus gravity, to the galaxy because we can see the effect of the gravity on the galaxy's rotation rate. We really don't know what the nature of the material is beyond that. Maybe it's normal everyday matter, just in a form that it emits so little light that we cannot see it. perhaps in the form of very dim stars or little black holes. More likely, though, it may be different types of particles we may not even understand yet.
So, does dark matter exist? The fact is, we aren't sure. Either it does exist, and we really are observing the effects of its gravitational attraction, even though we can't see the material itself and don't yet have the technology to detect it, or maybe there's just something else that we are misunderstanding, making us believe that this matter is out there when it really isn't. A lot of research is currently being conducted in the area of dark matter and another similar topic, dark energy. In the coming years, we'll probably understand what's going on much more clearly.
So far, we've looked at lots of images of individual galaxies, but galaxies don't usually live alone. They're almost always appearing in larger structures consisting of multiple galaxies. We use two different terms, group and cluster, to describe how many and what type the dominant galaxies in the set have. Spiral galaxies are often found in small groups of galaxies, up to a few dozen galaxies in each group. Here you see 3 large spirals with several small galaxies around. This group includes 3 large members as well: our Milky Way galaxy, M31, the Andromeda galaxy, and M33, the Triangulum galaxy. There are also lots of small galaxies called satellite galaxies that orbit around each of the larger ones. This is called our local group. In the PowerPoint on this slide, you can view an animation of how the galaxies in our local group move. While spirals are often found in small groups, ellipticals are usually found in huge clusters. Instead of dozens of galaxies that make up a group, typically hundreds or thousands of galaxies make up a cluster or a supercluster. Here we see a deep image of very distant galaxies. The farther away we're looking, the farther back in time we're seeing. This is a picture showing how the universe looked very long ago. This light has been traveling for a long time and is just now reaching us. So though the light is very old, the picture shows how the galaxies looked when they were very young. Since the Big Bang, which we'll talk about more in the next lecture, the universe has been expanding. In this graphic, you can see how the space between the galaxies continues to increase over time. In much the same way as the solar system developed from a nebula, a galaxy forms from an even larger cloud of material called a protogalactic cloud. These were made of hydrogen and helium, and the first stars that formed in the first galaxies condensed out of this material. These first stars were enormous and thus didn't live for very long. Constant supernova explosions kept these gas clouds churning and not able to form stars. The leftover gas ended up settling out into a disk, much like a spinning ball of pizza dough stretches out into a disk. But if all galaxies start out the same way, why do they come out looking so differently? Some have arms and others don't, in addition to other differences. Think of regular clouds in the sky. They all form in similar ways, but no two clouds ever look identical due to the interaction of the air molecules in the atmosphere. Similarly, the initial spin and density of the clouds will affect the size of the disk and how widely spread the material is. If the cloud is dense, the inward gravitational force is the stronger force. The gas cloud will contract more than it spins, creating an elliptical. If the cloud is less dense, there isn't enough mass close enough together for gravity to dominate, and the spin will twist out the arms into a spiral. Some galaxies also have their shapes altered by galactic collisions. Here, individual stars probably don't collide very often due to the large amounts of space between the stars, but the shapes of the galaxies are dramatically altered as one galaxy passes through another, affected by the other galaxy's gravity. On the left, you see another galaxy merger. The image on the right is the two galactic nuclei zoomed in. Look how stretched out the arms from these two spiral galaxies are and how they're getting stretched apart. This may be how irregular galaxies are created, distorted by other galaxies. We use computer modeling to show how galaxies collide. Here is the first stage in a collision between two spirals. Below is the full series of images of how two spiral galaxies might interact and combine over time. First, they start to slide through each other. Then the arms get stretched out as the galaxy's gravity pulls on the stars. Eventually, they collapse into an elliptical. Collisions might explain why elliptical galaxies are found where many galaxies are close together. They may have started out as spirals, but after colliding with other galaxies, they settled into simpler shapes. Gravity pulls the bodies together. Many giant elliptical galaxies actually seem to have eaten other galaxies when viewed in infrared light. What looks like one galaxy actually has multiple galaxies within it and is ready to eat several more. We call this process galactic cannibalism. Some galaxies have what are called active galactic nuclei, or AGN. This small region within the center of the galaxy is unusually active over some part or even all of the electromagnetic spectrum. Galaxies are often classified as radio quiet or radio loud, depending on how much light in the radio wave part of the spectrum they are emitting. We assume that radio loud galaxies have actively feeding supermassive black holes at their centers. Luckily, our Milky Way is radio quiet, with our supermassive black hole, Sagittarius A star, not actively feeding, or our galaxy would be a much more dangerous place. Radio loud galaxies are easy to detect from very far away due to the large amounts of energy they release. They sometimes actually have jets of material that shoot out from their nuclei. There is a lot we still do not understand about these active galactic nuclei. Many of these active galactic nuclei are quasars, or quasi-stellar radio sources. These are some of the most distant objects in the observable universe, and though they are small, they shine many times brighter than ordinary galaxies. They are thought to perhaps be disks of gas falling into a supermassive black hole. Again, there is much we do not know about these distant galaxies, but over the coming years, we will probably learn quite a bit more, perhaps finding out that some of what we currently believe to be true may be incorrect, or that it is only the tip of the iceberg of what remains to be discovered. One thing we know for sure, though, is that these distant objects all have red-shifted spectral lines, which actually serves as a major piece of evidence for our last topic, the Big Bang Theory.